And there we go. Okay, so basically, I'm going to share my screen. I'm going to start. Oh, and as a matter of fact, I've already downloaded the PDF. Not the PDF, I'm sorry, the PowerPoint presentation on the S drive. So that's already there for you guys. And so I want to make sure I pick the right one. Share. Okay. Yeah, I did a few things this morning. Okay. Now, I'm going to go through the animation. Oh, sorry, slideshow from the beginning. Okay, so guys, last week we started seeing, how connections are put together and, designing tension members and all that. And today we're going to actually, go through the trouble of designing a connection and determining the number of bolts we need to design it. So I'm going to start off with a very general, Now, whenever you're doing a connection, you have to look at what we call the load. Oh, let me just get my annotate. Where's my? Oops, sorry. I want to get my annotate, and I can't seem to get it this morning. Where are my? Well, that's what I like about technology today. Usually, I just put my pointer up there, and I get a drawdown menu. Yeah, I won't be able to draw today. Look, guys. Oh, there we go. Annotate. There we go. Very okay. Now, guys. Okay, so basically, you'll see that you have to worry about the load transfer mechanism. In other words, how is the load going to get passed through the connection, and you make sure that every element that's in that connection has the necessary resistance to be able to have the whole body or the whole connection work properly. And go back to my mouse here. So basically, the first question you have to ask yourself, are the bolts in shear or in tension? Because the bolts have a different resistance if they are being resisted, or if they have to resist the force in shear, or if they have to resist in tension. Now, just so you guys, for example, let me just draw something. In other words, here's my bolt here, and all of a sudden I have something that's going across here like this, and all of a sudden this member is being pulled here, and therefore you can appreciate, and I'm going to take Kaylee's advice, I'm going to start changing colors, and you can appreciate that what the bolt is actually doing is that it's resisting this force here in shear, so therefore that would be a shear resistance that the bolt has to do. Now, as opposed to, if all of a sudden the bolt is being pulled away, and therefore now it's in tension, and therefore now the bolt has to be use the tension resistance of the bolts. Anyway, so that's what you have to first consider: is the bolt having to resist the force in a shear or in a tension? Now, let me clear. So now the second question is there a single shear plane or more than one? So because what happens is that if, for example, let me go back to this drawing here, and we might be able to use it. Go to, let's use a yellow, And so here right now, if there's only one here, and therefore the bolt has to resist everything right across here, the yellow is not very good. So in other words, that would be single shear. But if all of a sudden there's two, if there's two planes here, that will be double shear. And with the example, you'll start understanding when it's in single shear and in double shear, because you can appreciate that then the bolt will take the shear resistance here and the shear resistance here, and you can combine those two shear resistance to give you the total shear resistance that the bolt has. So that's the second thing you have to consider. And then the third thing you have to consider is the shear plane passing through the shank or through the threads of the bolt? Now, let me just clear this. Let me just clear my drawing because it looks like. Now, so guys, this is a bolt, Now, of course, this is, I'm just going to take this here. I like this, So this here is, of course, the head of the bolt. Now, this part here, this part here is called the shank. Oops. Okay, so this part here is called the shank. Okay, and this is the threaded part. Okay, now you can appreciate that if the shear force, let me just change color because this is not, okay. You can appreciate that if the shear force is going right through there, the bolt, then it's got all of this material to resist the shear. And if the shear force is going through here, then it only has this material. And believe it or not, this here is about 70, well it is, you'll see it's 70% of the material that you have here. So basically, so here, you actually lose about 30% of the resistance, okay? And that's why, now, if you're not sure whether it's going to be going through the shank or through the threads, in other words, are the threads going to be intercepted, then you simply design all your connections with the more conservative one. And if you're absolutely sure that all the shear force are going to be going through the shank, then of course you can take the higher value. Now, before I go on, does anybody have any questions? And feel free to jump in. Everybody okay with this so far? Okay. Now, let me go back to my mouse. Now, this is just to let you know that when you go on the job site, okay, these are what we call high-strength bolts, okay? Now, there are two high-strength bolts. There's the A325 and the A490. The A490 are stronger than the A325, but they are both considered high-strength bolts. So the most common bolts that we use, okay, is the A325. We don't necessarily go for the A490. These are the ones that we would normally specify, okay? And of course, now, they have tried to make some metric bolts, but as far as the metric bolts go, they're not being used in Canada, okay? So therefore, if it was a metric bolt, it would be A325M after that, or A490M. But like I said, you won't find any metric bolts in Canada, so you might as well use only imperial bolts. And the most common denominator, or diameter, I should say, that you have for bolts are 3/4 of an inch. So that's the one that you normally start with, and unless you've got some real constraint that you can't, put the bolts in. So this here, so if you specify an A325 bolt, well, if you got on the job site, you can appreciate that on the job site, it will be marked right on the head of the bolt head that it's an A325. And of course, if you specify an A40, it would be here, okay? So that's something that you should, you can see. And as a matter of fact, if you're ever inspecting a job and the guy is actually doing this, like, they will not, the guy that's doing the actual erection, he'll definitely be using A325. But one of your tasks, if you're there as an inspector, is to make absolutely sure. Now, when it becomes more critical, for example, if somebody decided to specify this and they're using this, well, this is much stronger, and therefore, whatever they're connecting is going to be much weaker than what was actually designed. That's all you have to watch out for. Okay, so this is just some general information, okay, on the bolts itself. Now, here I'm going to give you some information of when you're detailing, okay, when you're detailing a connection with, okay, minimum pitch, okay. The minimum distance between centers of holes shall be 2.7 times the diameter, okay? So if, okay, I'm trying to get my circles. Oops, I should have made it a little bit bigger, okay? So if I put if I have two here, right? So what they're saying here, okay, what they're saying here is that, let me go back and change my, excuse me. Okay, so this here and this here is the pitch. So therefore, if I'm specifying let's use metric of, okay, if I'm specifying a 3/4 inch bolt, well, let's use a 20 millimeter bolt, okay? So 20 millimeters means that the minimum distance here would be 2.7 times 20 millimeters. This would be the minimum distance that you should keep here is, of course, 2.7 times 20 would be 54 millimeters, okay? Now, that is the minimum, okay? What you should always do is that normally what we like to leave here, okay, and you'll see this in a lot of details, okay, we tend to leave 3 inches, okay?
Sorry, sir.
Yes.
Are you screen sharing?
You don't see the video? Yes.
For some reason, I see you.
Hold on, I'll start over. Let me just clear this. I haven't stopped this. Yes. Is anybody else having problems seeing the screen?
I see the PowerPoint.
Yeah, I see the PowerPoint here sketch too.
Yeah.
All right.
The only time I had a problem is that if I have a hyperlink, I'm going to have to minimize this and then put up on a hyperlink for the screen sharing. But I think so far.
Oh, yeah, I got it.
Okay, so sorry. Okay, so it's good.
Yeah, sorry.
Okay, so guys, so therefore that's so 3 inches is what we used to use in our days. Okay, and then of course that would be 76. So don't be shy to put 80 millimeters, you know, between these things. You know, like unless you start getting into like a very cramped area and you don't have very much room, okay, and you want to, like, you have no choice, then you've got to respect this minimum here of 2.7. But otherwise, you know, give yourself, if for example, if I've got all of a sudden this here like this, and I can put a hole there and a hole there and a hole there, and I can respect that the 80 millimeters, well, do that. In other words, take the space that you can. The more material even between, the better it is, okay? So that's the minimum. If ever you ask yourself, well, how small can I go? Well, it's 2.7 times the bolt diameter. That's all you have to remember. Now, minimum edge distance. Now, the way that I'm going to draw this again, okay? So the minimum edge distance, okay? Now, there's a table here, and I'm going to have to go out, unfortunately, because, like I said, the hyperlink doesn't work. I'm going to try this, guys. If you don't see the hyperlink, let me know. Say, yes, we don't see it. I'm going to go here. Does everybody see this table?
No.
No, okay, so that doesn't work. So what I'm going to do now is I'm going to stop sharing. I'm going to go share the table. Now everybody should see it. Am I correct?
Yep.
Okay, so guys, this table, okay, comes straight out of my handbook, okay? So in other words, what they're saying here, let me just go back to handbook tape. Now, what they're saying here is that, for example, these are the diameter of the bolts. Of course, like I said, they give it to you in metric here, but you should be working in imperial because they don't have any metric bolts. Now, I want to explain something at a sheared edge and at a rolled or sawed edge or edge cut with a, okay? Now, you can appreciate that sometimes you can take, for example, either a member or plate or anything, okay? And this is in plan view, and what they have a machine that will actually just cut off, like in other words, they'll have, like, for example, this is a plate, and they'll have a machine that's going to cut it off right there, with like just by punching through it. Now, because they're punching through it, in order to allow for any small deformations or whatever residual stresses get built because of that punching, you can appreciate that when it's at a sheared edge, the minimum distance, in other words, if all of a sudden this is the plate I would use, right? It's not that the plate is all crooked, it's just to account for the possibility of maybe some residual stresses here and some deformation. Well, then if I put a hole here, okay, they're saying that, well, this distance from there to there, if it's going to be sheared, should be at least 28. Now, guys, I never, like, if I'm going to, you know, like, if I'm going to put an edge distance in, like, for example, for a 3/4 inch bolt, okay, I will go 40, 45, you know, I will only worry about these if all of a sudden I have a problem with my spacing or I don't have the room to do it. And of course, now what they mean by rolled edge, so for example, if I have an angle iron here, angle irons are rolled, and therefore if I'm putting a bolt in my angle iron, well, in this case here, from here to here, because it's rolled, I can go down for a 3/4 inch bolt here. I can go, the smallest one I can go to is 25 millimeters. So this is something that you have to keep in mind. Like when you're really, really tight in what you're in the area that you're working in, then you have to respect these dimensions. If you're not tight, give yourself the room to do it properly, okay? And so now, like I said, these minimum edge distances have to be respected, and I normally go way above and beyond these minimums, okay? Now, okay, any questions so far before I go back to the PowerPoint regarding this?
Sir, I don't really understand the difference between the at sheared edge and the other column.
I'm sorry, repeat that, please.
Yeah, I don't really understand what's the difference between the at sheared edge, like that column, and the other one, the at rolled or sawn edges.
Oh no, what they're saying here is that, for example, okay, what they're saying here is that the only one that becomes critical is if they're cutting the material by shear. In other words, there's a shear, like the thing pushes down and shears. In other words, they're actually cutting by a shear force. So in other words, I have an angle here like this, okay? I have an angle here like this, okay? And all of a sudden they have a machine that actually will be able to, they wouldn't do this for an angle, but for plates, okay? And they actually punch right through the thing, and then this gets broken off by shear. So in other words, if that's the way that they're actually going to be producing or fabricating the pieces, I should say, then you have to worry about these higher edge distances. Now, one of the most common ways of cutting structural steel, I don't know if you've seen this, but it's with an acetylene torch, okay? So in other words, it's a gas, right? And then all they do is they'll burn right through here. And because you're actually cutting it with heat, well, heat doesn't, as a matter of fact, heat will relieve any stresses. So there's no stresses caused by that way of cutting the material. And then water jet, believe it or not, guys, okay, they are starting to, or they don't, like some companies actually have water jets to actually cut their steel. And I think, I'm trying to remember if the pressure, I'm trying to remember off the top of my head, but I think that the pressure that's coming out of that jet, okay, that water jet, the nozzle of those cutting machines, I think it's at least 15,000 PSI, okay? So they can actually cut steel now using a water jet, okay? So all these other methods that the fabricator will be using to actually cut his material, well, that doesn't leave any residual stresses along the cut line, and therefore you can reduce your edge distance. But if you know that he's going to be actually shearing off the material, well, then these are the materials that you have to use. Now, like always, if you're not sure what method he's going to use, then always provide, the more conservative values. If you have to, I would never in my head, like, let's put it at 32. I would go to 40, 35, instead. I wouldn't even worry about 32. As a matter of fact, I'd use multiples of 5, you understand? So therefore, I wouldn't even use it. But if ever I'm in a situation where I have a very, very tight spot, and then I can't even I can only allow 25 millimeters, because that's all I have in terms of room, on my drawing, I will specify that all materials are supposed to be either saw cut or, torch, like no shearing. In other words, I would put in my specifications, no shearing of material, and therefore I know that I will be able to have or allow myself this year. So, and like I said, this is something that very rarely you'll come to this table to look at these minimums. The only time I come to this table is that I'm very, very restricted, very, very confined. I have not very much room. The member that I'm trying to connect is very small, and therefore I will come here and make sure I at least conform to these minimum distances. Okay, and again, guys, these are edge distances. Okay, I'm sorry, this is incorrect here. This is not an edge, and this is not this is an edge distance. Okay, so there's one for edge distances, and then there's one for end distances. Okay, so before I go on, any questions on this table? I think it's pretty straightforward, and let me just go and clear my drawing again. And sorry, Kaylee, I should have switched colors. Okay, so now let me stop sharing this and go back to the.
So far, so good, sir. It's okay.
Thank you, and then please, like, guys, at any time, because from my end, I don't see what's happening at your end, So let me go back to this, share. Okay, so. Okay, so here. Now, guys, okay, look. Now, I'm gonna do the animation because the slideshow from current slide. Okay. Now, remember, where is mine? Okay, there we go. Annotate. Okay. So, okay, I should have done this first. Okay. So now, just so that you guys appreciate the difference between edge and maximum end distance. Okay, so for example, let me just draw something here for you so you guys can see it. Where's the, there we go. Okay, there we go. Okay, so basically, this could be an angle, it can be anything. So in other words, if this is my member here, okay, so if I have a hole here, okay, from here to here, that's an edge distance, okay, and from here to here, that's an end distance, okay. So this is the end, and therefore the maximum distance from center of bolt to any of the nearest edge shall be 12 times the thickness of the outside connected part, but no greater than 150. So they even give you a maximum distance that you can go from, oh, the edge distance. Sorry. I'm really down deep at that. Sorry about that. Let me clear this again. Clear drawings. Okay. So here they give you a minimum edge distance. Okay. As you saw on the table. Okay. And now they also give you a maximum edge distance of 12 times the thickness of the outside connected part, but no greater than 150. So you can't go further than 150. So they even have some maximum edge distances. Sorry about that. Now, minimum end distance, this is what I want to talk about, okay? In a connection of tension members having no more than 2 bolts in a line parallel to the direction of loading, okay? So let's just talk about that so you can visually see what's happening, okay? So here is a tension member, in other words, okay? It's being pulled this way, okay, TF, okay? And let me go and change color for the blue. Okay, in a connection, a tension member having more than 2 bolts in the line parallel to the direction of force. So if I have more than 2 bolts, one, in other words, I have 3 bolts here. So now this is the direction, and therefore all the 3 bolts are lined up in the direction that the force is applied. In a connection where the members have more than 2 bolts in line parallel to the direction of load, the minimum end distance from the center of the end fastener, in other words, this would be the end fastener here. That would be the end fastener of the connection shall be governed by the edge distance in table 6. Okay, so therefore you go back to table 6, and that would give you the end distance. Okay? In members having 1 or 2 bolts in line, in other words, if I have a situation where I only have 2 bolts, okay, so therefore because I only have, and guys, never do a 1 bolt connection, always have at least 2. Okay, even if you only need 1 bolt, have 2. Okay, that's the good practice. The only time that I would have a 1 bolt, I don't know if you remember from the last lecture when we had those big pin connections, a big pin that's going right through the connection, that would be 1 bolt. But otherwise, always provide at least 2 bolts. Now, having 1 or 2 bolts in line of the load, okay, the end distance should not be less than 1.5 times the diameter of the bolt. So therefore, this one has the distance here. So therefore, you're looking at, okay, so if I have, I'm going to say 19 millimeters, a 3/4 inch bolt, I'll use 20 because it's easier to multiply by 20. Therefore, I know if I'm using a 3/4 inch bolt, I should have at least 30 millimeters here from the center line. And guys, these distances are always from the center of the hole to the edge, from the center of the hole to the edge. It's not from the edge of the hole to the edge. So, okay, and therefore, you just have to keep in mind that this has to be 1.5 times the diameter of your bolt. Not of your hole, of your bolt. So far, so good, guys? I guess if I don't hear yes or no, I guess I can go on.
Yep.
Okay, now this guy, I gave you this because I took this out of my handbook. Okay, this is just to show you that when you have profiles or shapes, right, and you need to connect them to other things, okay, they're giving you what they suggest as being the gauge distance if you're putting 2 bolts across this flange here, and the gauge distance here, okay. Now the reason why they give you these gauge distances, it's more a question of that when they're actually going to be tightening the nut, okay, or tightening the bolt, that there's enough room between, like, I don't know if you guys, like they have these open wrenches to, I don't know if you guys work with tools a lot, but you have open wrenches that you can use to tighten bolts. but the most common thing that they have is like a ratchet. It's like a socket. So they want you to keep these gauge distances so that if the guy wants to use a socket and like a socket, and he'll be able to put a socket in here to be able to tighten the nut, okay? And that's why they recommend these, you know, these edge distances, so that when it comes to actually erecting it, they'll have the room to tighten that nut. Now, if for whatever reason you can't respect these and the guy has to go in there, there's always a possibility that I don't know if you've seen these wrenches, but they look like this. They call them, they're just open wrenches. Okay, they look like this, you know what I'm saying? And those are open wrenches. They can use those too, but they prefer to use a socket, because the sockets, they have these electric, you know, sockets that they actually spin and everything else. So this table will guide you if ever you need to connect S shapes, W shapes, channels, and you want to connect them across the flanges, okay? What are the gauge distances that you have to, okay? That you have to maintain so that it's easier for them to actually erect your structure. Okay, so clear all drawing. Go back to notes. So I gave you this. You can have this in your notes. And of course, one of the most common things that we always connect are steel angles. And then of course here they're showing you the gauge distances. And of course this is a steel angle. That's what we call this an unequal edge steel angle. Okay. So therefore, here they're telling you, for example, if the leg measures 200 millimeters here, in other words, from there to there, you got 200 millimeters, then you can go up to M36 bolt and you can keep the gauge distance, okay? If this is 200 millimeters, you can keep the gauge distance at 115 and G1 and G2 in this direction. So this applies to whether your steel angle is what we call a steel angle with equal legs, okay? This applies to the leg itself. So even if I have an equal leg, if this is 200 here, okay, you can use these values here. And if this is 200 here, you can use those values here. And if you happen to use an unequal leg steel angle, okay, then you're gonna have to, like, if this is 100, well, it's really 104, but if this is 100 by 200, then for this one here, I would have to use the values that I have here, okay? So that's something else to help you, to guide you on, you know, how to space your holes in the members. So this is just information. Now, here, guys, don't panic, okay? These are the formulas, okay? So I'm giving you the formulas, but believe it or not, we're going to be doing everything by tables, okay? So now, I gave you the formula here because I want you to, like, for example, if I want to calculate, let me just go back to my drawing here, okay? If I have a bolt, okay? If I have a bolt here, okay? And the bolt is fastening one piece here and one piece there. So that's what it's fastening, okay? So, and the force is going like this, and the force is going like that, okay? Now, let me just change color. Now, you can appreciate that here, what happens is that now what's happening is that the force is going here, it's getting transferred right here, and then it's going into this member. So therefore, the force is being transferred by shear, okay? And here, there's only one shear plane that the force is being transferred. So therefore, here what you have is that you have a reduction factor, and of course the reduction factor is 0.8 here, okay? Then N is the number of bolts. So for example, if I have 3 bolts here, therefore I will multiply by 3. M is the number of shear plane, and in this case here, N would be 1 for this situation. AB is the area of the bolt, okay? And FU is the ultimate tensile strength of the bolt. And trust me, these things are pretty high, okay? Now, this is where, for example, this equation here, let me just clear this up a bit, clear all drawings, okay? This equation here, of course, is, if you remember the very beginning where you shear on bolts with threads excluded in the shear plane. So if you remember at the very beginning, we had, like here was our bolt, okay? And then we had one section that was threaded, okay? Sorry for my lousy threads. So in other words, your shear plane is going right through there, and therefore you use this equation here. Now, if the shear on the bolts with threads intercepted, in other words, if it's going through the threads, the only thing that changes is this chain goes to 42. Now, guys, what's 0.6 times 0.7? You can appreciate that all this means is that when you get here, the amount of material that's left here going across the threads is only 70% of what's here. So therefore, you have to actually reduce this by 70%, and that's why this goes from 0.6 to 0.42. Okay. Now, this is if you happen to have long joints, you have to use a reduction factor. I won't get into that because we're not going to get into that ourselves. Okay. And bearing. Okay. First of all, I'm going to explain to you what bearing is. Okay, bearing means that one surface is pushing against another surface. So for example, if I have a bolt here, okay, and I have a plate here like this, okay, and it's going there, and I have a plate here like this, and it's going there, okay. So what's happening is, let me just change color so in case we need to explain something. So what's happening here is that this force here, okay, is actually using this surface here to be able to transfer that force into the bolt. So that's the bearing area of the plate here. And then you have a force going this way, and therefore on this side, what's happening here is that it is bearing onto that surface there, so it can transfer it to this side of the connection. So therefore, you have to make sure that when you're designing your connection, that there's enough material here, so that all of a sudden, when the force is when this member is pushing, the surface of this member here is pushing against the bolt, okay, that this thing does not yield or does not, it doesn't deform. And therefore, this is the equation that you use to calculate bearing. Now, we won't be using the equation for this. We won't be using the equation for this. We'll be using all the values given to us in the tables, so don't worry about it. And then, of course, ultimately, if I happen to have, okay, a bolt, okay, and the bolt is actually resisting the force in tension, right, instead of shear, well, that's how you calculate the factor tensile resistance of the bolt. And as far as this goes, this is just a reduction factor. I gave you the values here for bearing, and I gave you the value here for the bolt itself. N is a number of bolts. AB is the area of the bolt, and F. Okay. So therefore, this is the equations. If ever you want to calculate them, I don't see why. I will give you the tables with these values already in them, and so clear all drawings. Go on. Now, this is where you would, all these values that you see here in the equations, okay, this is the first table. This table will be given to you. So this means is that if let's talk about a 3/4 inch bolt. Let's talk about a 3/4 inch bolt, because those are the most common bolts that we tend to specify. So for example, if I look at a 3/4 inch bolt, so in other words, like we have these metric values, like I said, they're not available in Canada. So maybe when you guys get to my age, everything will be metric. They'll finally get rid of the whole imperial system. But in the meantime, let's just worry about the imperial. So therefore, if you want to know what the area of a 3/4 inch bolt, well, there's the area. It's 285 square millimeters. So that's where you can find the area. Now, that first equation where we had the VR value, well, there it goes. It tells you that, okay, it tells you that for an A325 bolt, okay, the VR value that you would get for in that equation, of course, you would have to use a value of N in the equation. This would be per bolt. Gives you a resistance of 113 kilonewtons. So for each bolt, you'll be able to develop up to 113 kilonewtons. Now, this is where I want to show you the appreciation between an A325 and A490. See how much higher the A490 is, okay? So, and then of course they still have the N values here, but like I said, and the A307, guys, that's another bolt, but that's not a high strength bolt. And these bolts are usually used for anchor bolts, okay? So that's why they give you the values for the A305. But the ones that are the most commonly used are always the A325, okay? A325. So here, if you see, for example, now they've given you the value here, and if anybody wants to just test the table, take this value here, multiply it by 0.7, and you should be getting that value there. So instead of you having to do calculation, that these values have already been calculated. And again, okay? Now this is for shear, single shear. Now if you happen to have two shear planes, of course you can multiply these by 2. And this is for TR. In other words, if your bolt is in tension, well, you can appreciate that the tension resistance of a bolt, okay, is higher than the shear resistance, okay? For the same diameter, you get more tensile resistance than you have in shear, okay? And of course, if you're using A409, the tensile resistance is always higher than the shear resistance. So these, like, so for example, in a problem, I can tell you, well, the threads are excluded. So therefore, if I tell you the threads are excluded, I expect you to use this value. If I tell you that the threads are intercepted, then I expect you to use this value. That's the only thing I have to be careful. And if you're not sure in your design, guys, if threads are going to be excluded or intercepted, always use these values here, okay? Always, okay? Use these values here when you're not sure whether it's going to be intercepted or not, okay? And this way, if they're not intercepted, well, your connection is going that much more safely. Is this table clear to everybody? Any questions?
No,
Jump
sir.
in. Sorry? Oh, good.
Yeah, just one question.
Yeah, go ahead.
If you don't specify excluded or intercepted, then we always use intercepted.
I always say that if I don't specify whether the threads are going to be excluded or intercepted, you should always use intercepted.
Okay, and it's always 325.
And always use the A325 because that's the most common bolt. Understand?
Yeah. And what did you say about multiplying by 0.7? Which
Oh,
number?
yeah, always look. Just like it. Let me go back. Okay. I talked about this at the beginning. Like the only difference between this equation here and this equation here, okay, is that this is all the same. That's all the same. Okay. The only difference is that this is 0.6 and this is 0.42. Now, I told you that when you look at the threaded section of a bolt, that only has 70% of the material of the shank. Therefore, if you take this and multiply by 0.70, what do you get? You get 0.42. Now, the same thing applies here. For example, if I take 113, try it yourself. Take 113 multiplied by 0.7, you'll see you'll get exactly the same value there. So in other words, they're giving you the two different resistances depending where the shear plane is actually going across, okay?
Perfect, thank you.
Okay, and then keep in mind that when they're actually calculating the tensile strength, it's always based on the threads being intercepted because the tension, it's always going to be there. That's why these values seem to be, they're always higher in shear, but they're actually, like if you want to compare the tensile resistance of a bolt with the shear, you should be comparing this number with this number, not that number with that number, because this is what they're actually using. They're using a smaller diameter to calculate that TR value, okay?
Thank you.
Okay. So before I go on, anybody else with this table? Okay, so now let's go on. Now, that BR value, this is where you get the bearing resistance. So instead of you having to calculate it, okay, this is where, so in other words, they have different tables in the handbooks, and I gave you the one for the steel that we're going to be using, 350W, okay? Even for using the American steel, which is 345, trust me, this is accurate enough. So 300W, 350W. Okay, so basically what they're saying here is that if I'm using, now this is the thickness of the material that the bolt is bearing against. Okay, so let's just do that. Okay, so here is the material. Here is the bolt going across the material. Now I should, if I erase that, it's not going to work. Okay, so here's the bolt. Okay. Okay, so basically, this here is this thickness here, T. Okay, so in other words, sometimes you'll know the thickness of the material because you're going to be using a certain angle or whatever, so you know the T value. You can go straight here, come to take the T value, and then you can go across, depending on the size of the bolt, okay, you can get what's going to be the BR value. So for example, if this here is like this, okay, and you get a force acting here, and you want to know what the BR value, let me just change color. Purple, I never tried purple, okay. So if you want to calculate the BR value, in other words, how much resistance you would get when the material is bearing against a bolt, okay? Well, if I have a 10 millimeter plate and I'm using a 3/4 inch bolt, then the BR value is 206 kilonewtons per bolt. And therefore, if I have 4 bolts, I can take that 206 and multiply by 3. So that would be 618 kilonewtons of resistance in bearing.
Sir?
So that's this table very quickly gives you the values. I'm going to go back. Okay.
Sir?
Yes.
Does this apply for, like if this was wood being bolted? Are these the
Okay.
same values?
No. This is steel on steel. And
Steel on steel, okay.
Andrew, not only is it steel on steel, it's also this strength of steel. There are different tables for different strengths. Okay.
Okay,
So the thing is that, like, I gave you here the steel that we typically use in structural steel, like 300W for the plates, 350 for our profiles, right? WT because that's the doesn't make a difference. So this is for, as a matter of fact, this is for only this type of steel.
Okay.
So in other words, if you would have, there are steels out there that are stronger, therefore they would have a different table. There are steels out there that are weaker, therefore they have different values. So this, not only is this for steel, this is just for this strength of steel.
Okay, thank you.
Okay, and Andrew, just to let you know, I think it's next week or the week after, we will be doing it for wood, and you'll see the wood has a totally different, you know, I will be giving you the values for wood.
Okay,
Okay,
thanks.
so, okay, so this is just steel on steel, and not only steel on steel, but also this strength of steel and this specific steel. Okay, good question, Andrew. Clear all drawings. Okay, now, I guess the best way to do this, okay, oh yeah, if ever you have a situation where you have both shear and tension, okay, and guys, that would happen very rarely. That happens, for example, in anchor bolts that have a brace on it. But if ever you have both shear and tension, then there's this interaction equation here that you can use, where you take your VF value, your VR value from the table, your TF value from your analysis, your TR value, just like any interaction, you square them. And if these two ratios are less than 1, then you know that the situation is adequate. So I'm just giving you the equation in case that you ever come across the situation. Like, for example, where I'll draw you an example where this can happen. For example, many times you have bolts here. Okay, I'll just draw them very quickly. Okay. And you'll have a brace here that's in tension. So therefore, what's going to happen is that this brace will not only give a shear force to your bolts. Let me just change the color here. Will not only give a shear force, but this element here is also going to give you a tensile force to your bolt. So therefore, here you have both a tension and a shear in your bolt, and therefore you would have to use this equation in order to solve your problem. But that's, like I said, that is very rare. Most of the time it's just tension or shear, but if ever you have a situation that you do have two components acting on a bolt, then you have to use this interaction. And that's the only difference. So I'm giving you so you can have this in your notes. And that's it. Okay, the elliptical interaction equation was developed from test results. So like I'm telling you guys, a lot of the stuff that we have, okay, they do the tests, they correlate the values, and then they try to come up with a mathematical way of using it for our purposes in design. That's it. Okay, now guys, here we're going to start a nice example, okay, so that we can, okay, so we're going to start a nice example so that, excuse me, so that we can start understanding how to use this, okay. So for example, here, I don't know if you guys can understand what I'm drawing here, okay? So this, guys, in the old days, okay, when they would make trusses, okay? Trusses in the old days were made like this. In other words, they would either have 2 angles as the bottom chord, 2 angles as the web member, the vertical web members, 2 angles as the diagonal web members, and so on. And therefore, you know, like you would have to decide, like, how many bolts do I need to put across here so that I can make my connection properly, okay? And you can appreciate that these bolts here, okay, would be subjected to both a tensile force and a shear force because of this, okay? But for this member here, it's only a tensile force. So now, we're going to be using 3/4 inch A325 bolts. Okay, threads excluded. Okay, so in other words, here I'm going to remember, guys, you're allowed to design with threads excluded. In other words, you tell the erector or the guy that's going to be fabricating, especially the erector, because when you say threads excluded, he's going to make sure that he buys the right bolts, whereby the shank. Let me just draw this. Okay, so if we say threads excluded, then the guy's going to come, and so here he's going to buy the bolt so that he's going to make sure that that the shank of his bolt, right? The shank of his bolt is the same distance as the material that he's bolting. Okay, and therefore this means that the threads would only start right there, and then the nut. Of course, there's a washer. I forgot to talk about this, but you put a washer and then you put a nut over that. So that means that here, all the material is going through that connection where the, because this is where the, let me just change color for everybody. So in other words, this is where the shear planes would be, right here and right here. You would make sure that across those two shear planes right there, that he's going right through the shank and not through the threaded part of the bolt. So here I'm saying threads excluded. And you do that because, of course, you want to take the full strength of the bolt can provide. And that's why sometimes you do that. And sometimes it can be because you don't have enough room in here to actually do it with the threads included. So that's what we're looking at. Now, before I go on, clear drawing. Okay. Now, guys, this here, okay, I want you guys, I know some of you have trouble, okay? But what's happening right here, okay, is this here is looking, I'm going to try to draw it here, okay? It's as if I am looking, I'm taking a cross section and I'm looking right across there. Now, so in other words, if I'm looking this way, okay, what I see here, I see one angle, but then on the other side I have two angles. So in other words, I have two angles here, one beside the other. And then this is a gusset plate here that represents that thing here. And these are the two angles that form the bottom core. So I hope you guys can relate to the cross section. And what's happening is that 630 kilonewton of force is being resisted by 1, 2. So in other words, it would be 315 in this one and 315 in that one. Okay? Now, is anybody having problems seeing the drawings? And I'll go over it if you want. If not, I'll just clear this.
Yeah, sir. I'm having a bit of trouble.
Visualizing it?
Yeah.
Okay. So okay. So put yourself look at it as if you're standing right here. Okay. Or let's say I'm going to be cutting the stuff right there. Okay. So what's happening is like all of this is gone, right? And what I'm looking at is I'm looking this way. I'm looking this way. So when I'm looking this way, see this angle here? Okay?
Yeah.
This is the angle here. Do you see that?
Yeah, yeah.
Now keep in mind that right behind it, you won't see it in elevation, but right behind it, there's another one that's exactly the same as this one.
Okay, so there's two on top.
Yeah, there's
Then they
two
cut them
side
up.
by side. No, not on top. Two side by side.
Okay.
So this is so this one here is the one here. And the number 2 that you don't see because it's right on top of each other, it's in elevation, this would be number 2 here.
And then it would be the same for the bottom, right?
Exactly, the same thing happened at the bottom. Now this would be number 1, and therefore this is number 1 here. Okay.
Okay.
And then this is number 2 that you don't see, that would be number 2. And all this stuff in between, this is your gusset plate right here. So this would represent all of this over here. That a little clearer?
That thing in the middle, right?
Yeah, that's the gusset plate. That's the thing in the middle. That's what's using to make sure the whole joint works together.
Okay, now it makes sense.
So just to be absolutely sure, that section is going through the middle of the bolts of that vertical member, right?
No. What I'm doing here is that, because I haven't done it yet, but here there would be some bolt holes. You understand? So what I'm doing is I'm already showing you that you're going to have some bolt holes across that.
Okay.
I apologize. I should have I should have maybe drawn a couple of bolt holes, but this is just to show you that eventually you're going to have some bolt holes going across those two angles and the gusset plate. Sorry, Andrew, but you're right.
No worries. Thank you.
It's a little confusing because I don't show the bolts on the elevation, but yet I show the bolt holes in the section. I appreciate what you're saying. So I might correct that. I might put the bolt holes in next time, and this way it'll be less confusing. How's that?
Good stuff. Thanks.
Thank you for the comment. Okay. Okay. So now, this is what we have, and it's nice that we all understand the little drawing. Okay. So now, if I go back to my first slide, right? Does the first slide pop up on everybody? Does everybody see the load transfer mechanism?
Yes.
Yes.
Okay, okay. So in other words, this is where, to go back to this one, load transfer mechanism, to design or analyze a connection, the load transfer, okay. So are the bolts in shear or in tension? So can anybody answer that? The bolts that are going to be used to connect the angles to the plate, are they going to be acting in shear or in tension?
Shear.
Shear.
Yeah, I'm sure.
That's right. So, okay. Is there a single shear plane or more?
More.
Yeah, in other words, there's more because you have one that's going through one angle and one that's going through the other angle. So therefore you have more than one shear plane. Now, is the shear plane passing through the shank or the threads? And of course, here I said that the threads are excluded. Therefore, we know it's going through the shank. So those are three questions you should always ask yourself when you're designing a connection. Let me go back to the last view. Are we all back on the, is everybody okay with that? Okay. So now, so therefore, what's always our design objective? Of course, we want to make sure that the shear resistance here of the bolt is stronger than the tensile force that the bolts are resisting, okay? We want to make sure that VR is greater than TF, okay? And therefore, this is going to make sure that everything in this connection will have at least a VR value that's greater than 630. So that's our design objective. Now, let me go back to, why do I want to go to slide number 7? Okay, so I'm sorry, did I say what size of bolt we had? 3/4 inch, right? That's what we're using in our example, 3/4 inch, if I'm not mistaken.
Yeah.
Yes.
Okay. Okay, so basically, the reason I come here is, guys, I just want to show you. So I'm using an A325 bolt. I'm using a 3/4 inch bolt, and therefore, per bolt, I have and I'm saying the threads are excluded. Therefore, per bolt, right? Per bolt will give me a VR value of 113 kilonewtons per bolt. Everybody follows that so far?
Yep.
This is my VR value for one bolt, and that's where I get the value from. Okay, so here I have a VR value of 113, right? Bolt, and of course, one shear plane. Then, depending on how many bolts I need and how many shear planes I need, that has to be greater than 630. So in other words, this is my equation, and I want to solve it to see how many bolts I will need to get a VR value greater than VF. So therefore, if I go on, I have 113, and of course, I have, this is what I'm trying to determine. Do I need 1 bolt, 2 bolts, 3 bolts? But I do know that I have 2 shear planes in this case, and therefore, when I do this, I solve this side. Of course, I end up with 2.8 bolts, and anybody that puts 2.8 bolts on their test, when we do the last test, I'll give you 0. It's got to be at least 3. Fair enough, okay? So therefore, this tells you, so therefore I'm going to be using 3 bolts, okay? And therefore, to be able to attach my angles, both my angles to my gusset plate, I will need at least 3 A325 3/4 inch bolts. Does anybody have any questions with this?
Yeah. Sorry. What is M?
M is the number of shear planes.
Okay. Thank you.
If you go back to, I can go back, Andrew, if you want, but if you go back to the slide where I show you the equation, right? Each variable in the equation, I give the definition. N is the number of bolts, M is the number of shear planes, and so on and so on. Okay.
Okay. And can you illustrate somewhere on those drawings where those 2 shear planes are?
Yeah,
Please?
I will do that right now. Thank you for asking. Okay, so right now, okay, you can appreciate that I'm going to be putting 3 bolts in here, right? Everybody sees that? Okay. No, we're not there yet. Okay. So those are the 3 bolts, and now, so now I would have 3 bolts in here, not 2. Okay. So here's one shear plane, Andrew, and here's another shear plane. The bolt would be here, like this. I'm sorry, I should, okay. And let me just change color again. So in other words, when this thing is pulling this way, right, this force is being transferred right across that shear plane of the bolt there and right across the shear plane of that bolt there. Therefore, I have 2 shear planes per bolt. Is that a little clearer, Andrew?
No, not really.
No? Okay, so let's see. How can we explain this? Okay. If I, let's see if I can draw this. Okay. Okay, do you see this force here being transmitted through this bolt, and this bolt?
Yeah.
You see that? That you see, right?
Mhm.
So let me just draw it on one side. Okay, so I have this angle here. Okay, this angle here. And, okay. And right now, here is my gusset plate. Fair enough.
Mhm.
And here, I'm going to change color again so that we can all see it properly. Okay. And here is my bolt. Just worry about one bolt for now, okay, Andrew? Okay.
Yep.
So can you appreciate that? Change color again, make it blue. Can you appreciate that this is what's pulling here, my TF, right?
Okay.
And this is my gusset plate here. Therefore, the shear plane between the bolt and is right here. Do you see that?
Yeah.
So that's one here, right? Now I'm going to go back to red. Now, on the other side of my gusset plate, I have another angle, another steel angle. You see that?
Okay.
So in other words, just so that you understand, this one represents this one,
Yep.
and this one represents that one. So if I go back and use the same color, now do you see the second shear plane across the bolt?
Okay.
So therefore, this bolt is being, so in other words, if I just draw the bolt itself, right? If I just draw the bolt itself, let's try it there, green, okay. It's being sheared here from one angle, and it's being sheared there from the other angle. So this line represents that angle, and this line represents that angle.
Okay.
So therefore, I have one shear plane, 2 shear planes.
Okay.
Okay. Now, Andrew, if you overlook the number of shear planes you have, don't worry about it. Because if you, let's say you've assumed 1 and you have 2, all that means is that you have twice what you actually need. So that's a good thing, okay? The
Right.
worst thing is that when you assume 2 and you only have 1, that's really bad. You follow? So guys, I was involved in this bridge in Nova Scotia where the guy designed all the connections with 2 shear planes, and in reality, he only had 1. What a major screw up, okay? But that was only one of the major screw ups. The whole thing cost over $3 million to fix, but just to make you understand. So therefore, Andrew, if you're not sure if you have 1 or 2, if you take 1 and you happen to have 2, hey, you'll only be twice as strong as far as the bolts go. So you might end up with more bolts than you actually have. So in other words, if here I would have used 1 shear plane instead of 2, I would have ended up with 6 bolts instead of just 3. You follow what I'm saying?
Yeah.
And that's it, okay? I hope that's a little clearer.
Yeah, thank you.
Okay. Okay, so now we know that we need at least 3 bolts. Now let's go ahead and look at, okay, now, there's something I want to talk to you about, which you're going to, and that's called, let me just close this because it's in the way, okay. It's called shear lag, okay. Now this is a concept that a lot of people have a hard time understanding, but this is something that actually happens in members, okay. And, okay, so basically what shear lag is that if I have, let me just go back to my, I'm going to annotate, okay. I'm going to draw. Okay. Here, what happens is that I have, everybody sees the angle here. This is a cross section, right? In other words, this is a section taken across. Let me see which way should I be looking at it. I should be looking at it. And it doesn't matter. It's the same thing. Yeah. So I'm looking at it this way. Okay. So what's happening is that this here, of course, is this, and this here is the plate that's underneath. Okay. What happens is that when you have 2 legs, okay, when you have members where you're only going to be connecting one side of the member in your connection, what happens is that because of the lag that the stresses develop, okay? In other words, you can appreciate that. Look at it. Here the stresses are not uniform. And then as you're getting away from the connection, they become more and more uniform. And then eventually they become totally uniform. So in other words, from here to here, there's a lag period, okay? So in other words, it takes a while in order for this ununiform stress to become uniform. And every time we calculate stresses, guys, we always calculate it based on a uniform stress across the member. So what we have to do here is that when we have a situation where we know that the way that the member is connected, it's going to take a while before our forces become uniform. Because whenever we use that equation, TR is equal to phi ANFY, well, that's based on the fact that we're always looking at a uniformly distributed stress, okay? A uniform stress across the member. And therefore, there's the way that we do this is that we actually account for this, and I'll show you, and that's what this whole thing's about. So let me clear the drawing. Okay. So the shear lag, okay, not only, so for example here, if I'm going to be connecting, like you can see here, a plate, and this is a Y flange section. If I'm going to be connecting the top flange and the bottom flange to make my connection, well, the web member is not connected. Therefore, before the stresses become uniform in this connection, there's going to be a shear lag, and therefore I have to account for that. And don't worry about, oops, sorry. Why did I press escape? Slideshow. Okay, slide. Okay. So all you do there is that there are coefficients that we take into account into our equations, and that's what we're going to be learning. But I want you to just keep in mind why shear lag, what it actually means is that by the time the concentrated stresses at your connection, okay, become uniform across your member, whether it's, okay, so by the time these things here, okay, turn out to be this, okay, then you have to, either take the stresses and modify them, and that's what we're going to learn. And the same thing happens here. By the time these non-uniform stresses become uniform across here, then we will have to take that into account. So that's what shear lag is. And shear lag occurs whether the members are being connected with bolts, and we're going to have the same situation when we're going to be doing it with welds. So, but the formulas are slightly different, but the same concept applies. So now let me just clear this, clear the drawing, okay? And you'll see how we account for shear lag, but I want you to visualize what shear lag is, what it actually means. It actually means that the stresses will eventually become uniform in the member, and since this is how we always did all our equations based on a uniform stress across the member, well, we'll have to account for that by taking different values for the shear lag. So now it's not that complicated, but okay. Now, when fasteners transmit loads to each other of a cross-section elements of a member in tension in proportion to their respective areas, the effective net area shall be taken as a net area. So here, in other words, you calculate the net area and then you convert it into an effective net area, and this is where you multiply that by whatever factors accounts for the shear lag. So that's all they're saying here. When both transmit loads to the same, but not all the cross-sectional elements, then the critical net area includes the net area of the unconnected element, and the effective net area shall be taken into account. Okay. So, for example, if I have a W section, or a welded Y flange section, or an M section, which is a miscellaneous W section, or an S, which is an I section, okay? Okay, with flange width not less than 2/3 the depth, and for structural T's, okay, so if you're connecting Y flanges and structural T's, and you're connecting it at the flanges, well, whatever you're connecting, once you calculate your net area here, you would actually reduce it by 10%. In other words, you would multiply it by 0.9 to get your A and E value. That's all they're saying. Now this is if you're going to be connecting Y flanges. What we're going to be more concerned about, because the most common thing that we tend to use are angles, and therefore we'll be more concerned about angles. But if you are connecting Y flanges, here's the coefficient right here, that you have to multiply your net area by to get your actual net effective area for your calculations. Okay? Now, for angles connected by only one leg. So in our case, in our previous case, let me draw that, right? Let me draw that. In our example right now, we had, this was our angle here. Let me just see if I can draw it properly. This was our angle here, okay? And we had our gusset plate here, like this. And we had the bolt going across here. So this is one leg, right? And therefore, there's no connections in the second leg. Therefore, we would have angles connected with one leg only. If we would have another bolt here connected to something else, then we don't worry about shear lag because both legs are connected. Then we don't worry about it. But when we only have, okay, one leg connected, then we have to worry about shear lag, and that's what exactly was happening in our example here. Okay, so for 4 or more transverse lines of fasteners. So what they're saying here, let me draw this so that you guys can understand what's happening. So if I happen to have, okay, so here, I'll give you an example, okay. So here's my angle, okay. If, for example, I'm connecting it with 1, 2, 3, 4 bolts, okay, and this is the line of action. In other words, this is the line, the force is going, okay, so for 4 or more transverse lines of action, in other words, this is the line of action, this is 1 bolt, 2 bolts, transverse, 3 bolts, 4 bolts. Once I calculate my net areas in here, okay, once I calculate my net area, then the coefficient I multiply my AN by is 0.8. So that's when you have 4 or more bolts. Clear all drawings.
Sir?
Yes.
And that net area is just on the face that the fasteners are on, right?
No, the net area is the net area across where you're calculating the resistance for your connection, and we'll get into that. Okay. So the net area is like, remember what we did for the place when we were doing the tension, when we were doing the connections the first time I put you this? Well, I'll talk about the net area, okay? Now,
Okay.
if you have fewer than 4 transverse lines of fasteners, which is our example here, how many bolts did we decide to need for ours? We needed 3, right? So whatever net area we are going to calculate in our problem, okay, we will have to take that net area and multiply by 0.6 because we have, like, if we go back to our example now, okay, you remember this was the angle here, okay, like this, and we had 1 bolt, 2 bolts, 3 bolts, okay, so these were our 3 bolts here. Now, because we only have 3 bolts here and we only have 1 leg that's connected there, whatever net area I calculate, now, and it doesn't matter, okay, whatever net area I calculate here, I have to multiply that by 0.06, this coefficient, in order to take into account the shear lag that's happening in my connection. So, okay, now, for all other shapes, in other words, if you're dealing with anything else, okay, then the 3 or more transverse lines of fasteners, 0.85, okay, and for 2 lines, 0.75. So, like, this is what I'm going to be concentrating on because, like I said, angles are the most common thing that we use in bracing and stuff. So therefore, this is what I'm going to be concentrating on. If you're using any other type of shapes, well, you know that for a wide flange, it's 0.9, and everything else here is 0.75. Now, let's go on. Okay, so if we go back to our problem here, right? I'm going to go back to our problem here. Okay, now you notice, guys, okay, what I did, okay, you remember what we did this previously where I said, you know, like if you look at the end distance here, okay, like you could have gone to table 6 and so on, but I don't bother with that. Like I like to put, for example, I like to put, and let me just get this here. Okay, you'll notice that I put 80, 80, understand? I put 80 and 80. I didn't put 2.7 times the diameter of the bolt as being the space. In other words, 2.7 times 19 millimeters. I like to, you know, I like to give myself some room to make my connection. Here, I know that when I put this gusset plate here, I can basically, it's going to be sized on what my geometry here, so I'm not too worried about it. And here I have my end my end distance from my bolt to my gusset plate. Here I have my end distance from the bolt to the angle. So this here, guys, I do respect the 2.7 times the bolt diameter, because 2.7 times 19 is something like a little 50, whatever it is, 53. Therefore, by putting 80, I respect that. And I know that the edge distance here is the same as the for the. So therefore, I just make sure that my geometry, works out nicely. Now, so this is what I came up with in terms of spacing my bolts. And I know that these spacing will respect the values in table 6, and therefore I will not sweat over that. Now, step 1, right? We have to determine, step 1, we have to determine what size of angles are we going to have to use here, in order to resist this force. So step number 1. So what we're actually doing, what we're going to actually be doing is, we are going to assume that our first failure plane will be right across the member. So in other words, both these angles are going to fail, or we want to make sure that both these angles have sufficient resistance. Sorry, I just wanted. What time are we calling this a day? Both these angles have to have a resistance of at least 630, Therefore, I use the equation phi AG Fy should be greater than or equal to TF. And to be able to see how much of a cross-sectional area here I need, how much of an AG here I need, in order to provide a force of at least 630 kilonewtons. So therefore, I use this equation here. And therefore, I end up getting an AG value. So in other words, I need an AG value of at least 2,333 square millimeters. So therefore, these two angles combined should give me an area of at least 2,333 square meters. So I first determined what would be the minimum area I would need so that these two angles will give me the resistance to overcome or to resist this force here. Now, because I know that I have only 3 bolts in this connection, what I do is, oops, let me clear the drawing. What I do is I make an allowance, well, let me close it. I make an allowance for shear lag, Now, what I do is, of course, if I go back to this slide here, since I have fewer than 4 transverse lines, therefore, I would have to calculate my net area by 0.6. So therefore, what I'm going to do is, oops, sorry. So what I'm going to do now is right now, remember guys, these are all trial sections that whenever we're designing. So what I'm going to take my area and I'm going to divide it by 0.6 to see how much more area I'm going to be providing for my angles, so that when I do a total calculation across the bolts, I would have sufficient area in my angles. So I artificially increase my AG to what I should do, is that eventually when I look at the different failure planes, I'll account for the shear lag. So that's what I do here. And in other words, yes.
Sorry to bother you. For the transverse lines, that's dependent on the number of bolts, right?
Well, in other words, like let me just go to annotate, So in other words, so if, for example, I would have 1, 2, 3, 4 bolts, So in other words here, and these are the transverse lines of bolts, right? And this is the force here. Everybody follows? Now, if I would have 4, then I would use 0.8 here. But since I only have 3, they're telling me that I have to use that coefficient of 0.6. So 3 or less, I use 0.6. 4 or more, I use 0.8. Is that clear?
Right. Yeah, thank you, sir.
Okay. Now, let me go back to. Oops, I should use them. Now, this is the first time you guys are going to see these tables, and unfortunately, even though if I press on the hyperlink, you won't see the table, so I'm going to have to exit here. And I'm going to have to go and share screen with you. Okay, so we're looking for something that's got at least 3,880 square millimeters. So stop sharing, share screen, share. Okay, now guys, these are tables that I got for you straight out of the Steel Handbook, okay? And these are tables that for angles that are back to back, okay? I hope everybody sees these tables. So basically what we're looking for is like we're looking for a combination of steel angles whereby the total area will be about 3,880 square millimeters. It can be a little bit less, it can be a little bit more, but that should be the range. So therefore, if I look at these tables here, let me just get my annotate again. Okay, and I want to draw. Okay, so you can see that here is where you get the area. So you see that this would be way too big for our needs because it's got 21,600 square millimeters. We only need 388. And coming down here, well, this would maybe not be enough. Okay, so this could work. In other words, a 127 by 127. Okay, so if you want to use angles of equal legs, that can be one possibility there. And so you're looking for something in that range. You're not looking for an exact number because you can ultimately use less. I can maybe use an 89 by 89. So in other words, you're looking for angles that have approximately 3,800 and whatever it was, okay? It can be a little bit more, it can be a little bit less. If it's more, then you'd be on the conservative side. If it's a little bit less, it can still work. And let me just see if I can, excuse me. How come I only have one sheet here? Is there only one page? Yeah. So this is where, like, I'm going to be giving you, okay, like, I'm going to be giving you on the exam, or like, if you guys need these, I think I will be giving you, I will post whatever I have on the S drive of these two angles back to back so you can do the assignment and so on. So this is where you come and look for some angles. Like, I'll tell you what I'm going to be doing in the exam so I can narrow down your choices. But for now, if you were doing this in real life, you would actually start deciding, do I want to use, which one do I want to use? It's all up to you, basically. So, just let me check something. So basically, guys, like, I should have cleared the drawing. Okay, so I'm going to post these tables on the S drive. Well, first of all, they're posted in the lecture, so therefore you'll have them. If you go download the lecture, you'll automatically have these tables. So here are, like I said, so what you're basically, you don't care about these dimensions here, right here. All you care about is getting the areas. That's what you have to start to work with. And therefore, and you look for something that's in the order of, like, this could be a good choice here, 3,000, 89. So now I don't remember exactly what I chose here, but I think I chose something very close to 3,880. I'm going to stop sharing this. And I'm going to go back to the PowerPoint. Share, okay. Okay, so basically what I did is I took a 102, like, if you guys want, okay, I took a 102, this is two 102 by 76 by 11 millimeter, okay, and that gave me an area of 3,700 square millimeters. Let me go back to the slideshow. So this way it'd be less confusing, okay. So you'll notice that even though this is what I got, I ended up using something a little bit less because this is just to give me a ballpark area. It's not to give me an exact area, and I decided to go with something a little bit less, and therefore this is the angle that I decided to use to solve my problem. Now, what you have to do is you have to determine the possible failure planes, okay? Now, just to let you understand something, let me just go back here to annotate, okay? Now, you know that if we were doing this in reality, okay, in other words, this is one failure plane here. But what happens is that for that one failure plane to occur, I would need about this is what I would need for that failure plane to occur. And since I'm providing this amount of steel, therefore this will never occur there. That's why I don't check that failure plane. But I know that now my connection could fail right there. And it can block shear right here. Okay, so therefore, these are the two possible ways that this connection can fail. It will never fail here because to fail here, the area has to be smaller than 2,333 square millimeters, and I'm providing 3,720, so we'll never fail there, but it can fail there, and it can block shear here. So these are the two ones that we're looking at, and now we're gonna have to start doing the calculation like we did in the previous lecture. We have to start calculating our net areas and using the equations to see what our TR value is for failure plane number 1 and failure plane number 2. So, guys, clear all drawing. Okay. Go back to the mouse. So let's start with failure plane number 1. Okay. So determine TR for each failure plane. So what we'll do is for section 1-1. Now, this is the equation. Okay. So TR is equal to phi u A and E. Okay. The A and E is to account for the shear lag, and the FU is the ultimate tensile strength of the material, and that should be equal greater than 430. So now, I want to make sure that you guys can understand, like, first I calculate AN. So let me just draw this so you guys can understand what I'm doing, okay? So basically here's my angle, right? Oops, a little too thick. Let me just undo that. Here is my angle, okay? And here is my angle. Everybody follows? I have two angles back to back, right? And basically, I'm putting a hole here in my angle. So in other words, what's happening is I'm removing this amount of material from my one angle, and I'm removing this amount of material from the other angle. So that's what I'm actually removing. So therefore, I know that this angle and this angle has an area of 3,710 square millimeters. So that's the area of the whole cross section. So that's where this number comes from. Now, 19, we decided to use 3/4 inch bolts, and therefore the diameter is equal, the diameter of a 3/4 inch bolt is 19. Since I am not sure whether the holes are going to be punched by the fabricator or they're going to be drilled, therefore I make the allowance that the conservative one, I make the bolt hole actually, this is going to be the actual bolt hole. So in other words, I'm going to assume 19 plus 4. In other words, I'm going to assume that the bolt hole is 23 millimeters. And this here is the thickness of the hole that I'm removing. And therefore, that's the 11. And of course, because I have one there and one there, I have to multiply by 2 holes. Now, I want you guys to look at this and go over it, because this is probably the most complicated thing in these problems, and to be able to how to calculate your AN from the values that you have. Does anybody have any questions? Do you want me to go over it?
Sir, can you repeat that part again? I don't understand.
Yeah.
Okay.
Same here, please.
I'm going to repeat it. My pleasure. Hold on. Let me just change color, or maybe okay. Okay. Now, in other words, can you appreciate that if I wouldn't have any holes going through the angles, that my AN would be, ANG would be 3,710 square millimeters, okay? So that's how much steel I have here. In other words, that's how much steel I have here, here, and all over. So that's the total area of my steel. Now, when you're looking at, okay, let's go back. Let me go back so that I can, okay?
That's the area for both angles, right?
That's here for both angles, okay?
Okay, thank you.
So in other words, like right across here, if you guys can see where my pointer is, okay? Let me just put this on here. Right across here where I'm, okay? The area right across here for both angles is 3,710 square millimeters. Is everybody okay with that? That's the amount of steel I have going right across here if there was no holes in it. The same way that it would be right across here, anywhere across the two angles, I have a
If
total
there were
area.
no holes.
Pardon?
That's if there were no holes.
Yeah, exactly. In other words, if there was no bolt holes, you can appreciate that the two angles would give me a total cross-sectional area of 3,710 square millimeters. Is that okay so far? In other words,
Yeah.
let me put this in blue or purple. Okay, maybe you can see it here. And let me draw it, okay? So this here, all of this here, all like this cross section here of the angle here, in other words, and this cross section of the angle here, all of this here will give me a total area of 3,710 square millimeters. Is that okay with everybody? If there's somebody that doesn't understand, I'll try to find another way to explain it. But in other words, here, the total area at any section across the two angles gives me 3,710 square millimeters. Now, that's what I have across here. Now, what I need to do is I need to calculate how much do I lose here. In other words, let me change color. Let me put green. How much do I lose right across here? In other words, when I look at my two angles, sorry, when I look at my two angles like this, back to back, okay, at that one hole here, right across here, okay, that's going across those two angles. Okay, how much of that steel am I losing right across here? That's what I'm trying to determine. In other words, that will give me my A net across those two. And if I go back here, okay, now let me clear this drawing because it's becoming really messy. Okay, so what I'm doing here is I'm taking my bolt hole plus 4 millimeters, because if you remember from the lecture we did way back when you actually want to determine what size of hole you have, you take the diameter of the bolt, you add at least 2 millimeters, but if you're not sure if the hole is going to be drilled or punched, then you should take 4 millimeters, and that would give you the diameter of the hole. And then, of course, 11 is the thickness of the leg. In other words, this is the thickness of the angle. And since I have two holes, well, this is the total area. Let me just go back here. Okay, so this is the total area that, oh, I'm trying to draw it as quickly as possible. Change color. Okay, so this is the total area that I'm losing right there and right there. So this part of the equation here is giving me the total area of that little area there and that little area there. That's what I'm losing.
But sir,
Yes.
aren't you like assuming, since you're just basically taking the diameter of the bolts, aren't you
Yeah.
assuming that it's square?
Sorry, go ahead, Emily. Go repeat it.
Like you're assuming that the area of the bolts that you like the area of the like that you're subtracting, right? So is that like the holes from the bolts?
Oh, see, your question is not that clear to me. Look, what about if I draw it like this? Okay.
They're the holes for the bolts.
This is the diameter of your bolt. Okay. In other words, we use a 3/4 inch bolt, but you cannot make a 3/4 inch hole to put in a 3/4 inch bolt, Emily. Understand? In other words, look. Maybe you'll see it clearer. Okay. So let me see if I can draw it here. Okay. As if it's open. Okay. Now I'm going to do this for one angle, because if I do it for two angles, it's going to be harder to see, and then you just have to multiply by 2. Okay. So if you remember, if I have, for example, here, I have one bolt hole. Okay. Now, for this bolt hole here, the diameter of that bolt hole, okay, is going to be the diameter of the bolt, which is 19 millimeters in our case, because it's a 3/4 inch bolt. Now, the minimum size of the hole is going to be 2 millimeters. So if I know the guy will be drilling the holes, I just make an allowance for 2 millimeters. So therefore, this bolt diameter here will be 21. But since I'm not sure if it's going to be drilled or punched, then I have to add another 2 millimeters, and that becomes the diameter of the hole. So therefore, the total diameter of the hole comes out to be 19 plus 4. In other words, comes out to be 23. And then, so that's going to give me the length this way, right? So that gives me the length going across here. Okay. That gives me the length going across here. And then, of course, if I multiply that by the thickness of my angle, in other words, 11 millimeters, that will give me the area that I'm removing from one angle. And then, since I'm doing one hole in one side and one hole on the other side, well, then I have the same amount because this 3,700 here is the sum of this angle plus that angle. And therefore, I have to take away this hole plus that hole.
Okay, perfect. Thank you, sir.
Is that clear?
Yes.
Okay, so clear my drawing. Okay, so basically, now this is where, because, okay, what's happening is that now I calculated my net area, and because of shear lag, I have to get my net area and I have to get an effective net area, and that's where that coefficient of 0.6 comes into our equation here. So therefore, this was my net area here, and therefore this is where that 0.6 comes, and therefore this area now gets reduced to this much. That's how I account for shear lag, and therefore now I have the right value. I have the right A and E value, the effective net area. And of course, this is a reduction factor, and that's 0.75. And FU is the tensile strength of your steel, and that's taken as being 0.45. And when I multiply this all out, wow, I get a TR value of 648.7. And since 648.7 is bigger than my TF, I know that it won't fail across that hole. So therefore, I've checked that one, I'm satisfied. Now, I have to do the same thing for section 2.2. In other words, 2.2 now, I'm going to redraw this so that we're all on the same page, okay? And 2.2 now, okay? Remember that 2.2 was the one where this is, okay, we have a hole, okay? And we're saying that it's going to be a block shear. In other words, I should change colors. Okay, we're saying that it's going to fill there, and it's going to fill across here. So here it's going to fill in shear, and here it's going to fill in tension. So therefore, this part of the equation takes care of this failure plane, and this part of the equation takes care of this. It's the other way around. Let me erase all that. My mistake. Okay. So my mistake. So here. So in other words, here the material is being pulled in tension. This right across that failure plane. So therefore, this equation will take care of this. Let me erase this because this is incorrect. Okay. So this part of the equation takes care of that little failure plane up here. Let me just change color. Okay. So change color. Okay. So this equation will take care of the failure plane across there. Should put it in blue. So this is what's taking care of the failure plane there, and this is where it's shearing off. Okay, so this part of the equation here is calculating the resistance across there. Okay? So now here we'll talk about the different variables. Now here, in other words, AN, right? Now here, I want you to understand that, let me just erase the whole drawing so it's clear. Okay. Now, I'm going to have to redraw this. This would have been easier if I was on the board, but okay. So right now, I'm looking at the last hole here. And I'm trying to calculate the AN value across that little failure plane where everything's in tension. Okay, so if you remember the sketch, I had here an edge distance of 35. That's what I decided to set my geometry to do. So that's where the 35 comes from. 19 is, of course, the size of my bolt. Plus 4 is to make the allowance for the bolt hole, in other words, for punching. And then I only take half because it's only half the bolt diameter that I take away from that plane. So therefore, that's where that number comes out for. And of course, this is the thickness of the angles. In other words, that's that thickness there. And if I multiply by 2 angles, that's the amount of area that I lose across here. So that's going to give me my AN value for that little plane there. I have 517. Now my AG.
Sorry, where was that 11 from again?
That's the thickness, Andrew. This is always the thickness of your angles.
Okay. Okay. Thank you.
let me go back and put it so I can go back.
Sure.
Okay.
Sir, it's just
Good question.
confusing
No,
because
this is the 11 here, okay? Always a thickness, you understand?
Yeah, good. Thank you.
Okay, so that's the 11 there. That's the, and of course, because I have two angles, I have to multiply by 2, okay? Now, the AVG, of course, if you remember, I had here, the edge distance here was 45. And
Sure.
then I had 80 and 80, so therefore, the shearing across here is going to be 80 plus 80 plus 45. That's where I have this, okay? So that's where it's going to fill in shear. Let me just change color again, purple. In other words, this is where it's going to fill in shear, and therefore, I have to use this side of the equation. Now, 11 again is the thickness, and of course, I have two angles. So that's the total amount of area that I have to resist a shear force. Okay. Now, excuse me. Now, so I have right now, I have this value here, my AGV value, and I have my AN value, okay? So far, that's what we've calculated. So in other words, this is for this, and this was for that. Now, FY, of course, that's 300, and the FU is 450, or you can use 0.3 or 0.45. You take the average of the two. Now, this is the same FU here of 0.45. We'll talk about this here, the utility factor, okay? Let's talk
I have a
about
question.
that. Pardon? Yeah, go ahead.
I don't understand why you're dividing by 2 for AN.
I'm not dividing. Oh, the reason why I'm dividing by 2 is because, okay, this is my steel angle here, okay? Here's my hole, right? There's my hole, and there's my hole. You see that?
Yeah.
Now, let me just change color. We said that from the center of the hole, I decided to put an edge distance here of 35.
Mm-hmm.
Okay? You follow?
Mm-hmm.
Sounds good? Now, this 35 represents that dimension there, right?
Yes.
I want to be able to calculate what is the area I have here. I want to be able to calculate this area here. So therefore, how do I get that area? I take this length here and I subtract that distance there.
It's half your bolt.
Half the bolt hole.
Okay.
Is that clear?
Yeah.
Good for everybody? So that's where the half comes in, because I'm trying to find this little distance here to subtract it from that distance there. That's all I'm doing. So let's clear the drawing. Okay. So now we'll talk about this. So this here is something that, I gotta go to my mouse. Okay. Now this here, let me close this so that the T is the efficiency factor. UT1 is used for symmetric block or failures. Okay. So in other words, if you have something that's very symmetric, in other words, if you have a situation, let me just draw this so that you guys can appreciate this. Okay. Okay. So for example, if you have a situation where this is going to be the block out like this, in other words, the whole thing's going to come out. It's very symmetric. You can take a UT equal to 1.0. You can have a situation like that. That's what they mean. So in other words, when something is symmetric, in other words, it's going to fail there, it's going to fail there. That's a symmetric failure. Use 1. That's what they mean there. If not, then, okay. This is the UT values depending on what you're connecting. Okay, so for flange connection T's, you use 1. For angles by one leg and stem of connection of T's, in other words, this is what we're going to be using because this is what we have. We have connections. Okay, we have angles connected by one leg only and stem connected by of T. So in other words, I don't know if you guys, I can draw that for you if you want. So in other words, if I happen, you guys should know what a T is, okay? So for example, that's a T. If ever you're using a T section for whatever, and you're connecting across here, then you should be using 0.6 in your calculations for that type of connection. In our case here, we have, okay, we're connecting through one leg. Even though there's two angles, we're only connecting through one leg, and therefore our efficiency factor is going to be 0.6. So that's what we're going to be using our equation. Now, for coop beams, now, guys, coop beams, I'm going to explain to you what those are. And you'll see this more when we get into almost our last lecture, okay? Like when you have a connection, okay? For example, here's a column. Here's a column, okay? And we're gonna learn how to do these connections. And this is called an angle connection that you're going to be fastening to your column. And all of a sudden, you're going to have a beam in here that you are going to be connecting to the column, okay, like this. Fair enough. And this is how you're going to be connecting the beam to the column. This is an elevation, okay? Now, in order for them to drop the beam, and if I do a section across here, what's going to happen is that I'm going to try to draw you a section. So this is a section of the column. Here's one angle here. I won't draw the whole thickness. Here's another angle here. And basically what happens is that this web of this beam has to drop in here. Let me just change colors so that we're all on the same page. So this web here, okay, has to drop in here. So what they do is that in order to do that, they coop the beam. In other words, they cut this part off, and therefore you can drop the web right in between these two spaces. This is what they mean by a coop beam. In other words, they will cut off the bottom flange and part of the web. So when they're actually erecting this and the crane lowers the beam into this little hole here, it can go through without this interfering to be able to place it in the correct. So whenever you have a double angle collection, you always coop your beams if it's going to be dropped between two columns. So that's what they mean by coop beams. And you'll see this a little bit clearer when we actually do the double angle connection in our last lecture, I think. That's when we're going to be doing it. Clear drawing. Go on. And of course, if you have one bolt hole, one line of bolts, I should have kept my drawing. In other words, if you only have one line, it's 0.9. If you have two lines of bolts, very rare you'll have two lines of bolts for that kind of connection. Now, all we care about is that in our case, our efficiency factor is 0.6, and therefore that's the value we put here in the equation. And now we're ready to calculate our value of TR. And we end up with a value of TR of 847.3, which is greater than my TF, and therefore our failure plane will not occur because we have more resistance than the force required. And therefore that failure plane is okay. So now, the last thing we have to design is the gusset plate. In other words, how thick does the gusset plate have to be? Guys, am I going overboard? I am, right?
Yeah, almost.
Yeah, I
So
know.
do you mind continuing in the
7
lab?
minutes.
Yeah.
Okay, guys, look, I'll continue at 2 o'clock. How's that?
Yeah, 'cause
Perfect.
And I apologize because I told you I have a little clock here, but I never look at the time. I apologize for going over. But okay, we'll resume. Okay, before we all go off, I want to take a roll call here. So I'm going to escape, stop sharing. I have to take a roll call here. So before you guys go off, okay, it's I have to take a roll call very quickly to see who's here. So is Michael Blair here? Just say yes. Yes,
Yeah.
Michael, you're here. Thank you, Michael. Nicola.
Yeah.
The other Nicola.
Yep.
Oh, thank you. Emma.
Here.
Thank you. Shibo.
Yep.
Thank you. Giancarlo.
Here.
Thank you. Matthew Ray.
Here.
Thank you. Andrew.
Yeah.
Emily.
Here.
Okay, Subitan.
Here.
Thank you. Jared. Gianfranco.
Here.
The other Gianfranco.
Here.
Kaylee.
Here.
Thank you, Kaylee. Joel. Joel's not here? He's absent? Okay, so Joel is absent. Sorry. Okay, Vincent. I can't hear you, Vincent.
Sir, sorry, I was mute. I'm here.
You're here, Vincent?
No, Joel.
Sorry?
Joel. I was mute.
Joel, you're there?
Yeah, I was
Okay,
mute.
thank you. Thank you, Joel. Thank you for getting back here. So, Vincent, you're there?
Yeah, I'm there.
Thank you. Paige? Paige
Here.
is not Paige, yeah, Paige, you here? Thank you. Michelangelo,
Here.
you're there, Michelangelo? Thank you. Oh, and,
Yeah.
okay, so Michelangelo, you're there. Rochelle?
Yeah, I'm here.
Thank you, Rochelle. Santiago? Santiago's not there? Okay, so he's absent. Joseph?
I'm here, sir.
Thank you, Joseph. Ramelin? She's not there? Absent. Marco?
Here.
Thank you. Matthew?
Hi, sir.
All right. John Michael? John Michael's not there? Absent. Jaywad?
Here, sir.
Thank you, Jaywad. Tima?
Here.
Hey, Tima, where were you on Monday?
I'm sorry about that.
Oh, it's not my loss, it's yours. So, I'm glad you're here today, Tima. Ashley?
Here.
Thank you, Ashley. Kambale?
I'm here, sir.
Yeah, nice to have you come, Kambale. Sorry for, I heard the hard troubles you were having on Monday.
Yeah, Wi-Fi problem, sir.
Yeah, I know. I heard that you had also trouble getting into your inspection class. So I'm glad you were able to come on board.
Thank you. Thank you,
Vincent,
sir.
Vincent, you're there?
Yes, sir.
Thank you, Vincent. And Yasin,
Here, sir.
you're not last but not least. Okay, Yasin. So guys, I apologize. Like I said, I'm trying to give you the most of my time that I can. I will continue this in the lab at 2 o'clock, and then once we finish this, we will go on and do the lab. And then after that, like I set up a tutorial for 4 o'clock, and therefore I'll use that time period as a tutorial. So in the meantime, guys, stay safe, and we'll talk to you all guys at 2 o'clock. Sounds good?
You too.
Thanks.
Thank you,
Take
sir.
care, guys. Okay. Have a good. See you at 2, or talk to you at 2.